Take a look at the typical 40-foot water towers dotting the landscape of almost every rural town and city. We usually treat them as background noise, but physically they are massive structural anchors with largely untapped potential. Their baseline function relies entirely on height. By elevating a storage tank 40 feet in the air, the physical weight of the water column naturally creates 17.3 psi of hydrostatic pressure. That pushes water through local distribution lines entirely by gravity, completely eliminating the need for electric booster pumps. We can modify the roof of that tank with a passive radiative condensation array, or PDRC. By layering specialized optical films over the surface, the roof rapidly cools itself against the cold sink of deep space, passively condensing around 28,000 liters of clean drinking water out of the ambient atmosphere every year. Squeezing 28,000 liters of pressurized water from the sky is an excellent baseline. But the Neo-Pioneer model demands more from our civic infrastructure. The ultimate goal is to convert this tower into a fully independent micro-utility that replaces the local gas station entirely. Pushing this tower into the energy business reveals a harsh mathematical reality. Even with advanced modifications, the maximum peak electrical output a retrofitted 40-foot tower can generate is only 7.3 kilowatts. This chart compares our tower's peak generation capacity to the instant power demand of a modern Level 3 EV fast charger. The tower produces an average of 46 kilowatt-hours a day as a slow trickle, while an EV demands a massive 100 kilowatt burst the moment you plug it in. If you wired a fast-charging cable directly into the tower's electrical generation system, the instantaneous draw from the vehicle's battery management system would trigger a mechanical failure state, immediately overloading and frying the tower's electrical architecture. So, we face a specific engineering puzzle. How do you force a localized system, which only generates a tiny trickle of power, to safely deliver industrial-scale electrical pulses on demand? We do not actually have a power generation problem. The daily energy yield is sufficient for multiple vehicles. What we have is a severe energy bottleneck, requiring advanced buffering logic. We start by transforming the exterior of the tank. We install 18 curved composite aero-cowling vanes, bolted securely around the perimeter of the existing water reservoir. This diagram illustrates how these vanes function as an omnidirectional aero-stator. Instead of waiting for the wind to blow in a specific direction, the curved cowling captures ambient airflow from any angle and accelerates it into a central vertical axis rotor hidden inside the cage. Funneling the wind inward strips away convective turbulence from the outer edges, which shields the delicate water-condensing PDRC roof from heat-stripping wind shear. We then laminate marine-grade bifacial solar cells directly onto the exterior skin of those curved aero vanes. This allows the fins to capture both direct sunlight and high-albedo reflections bouncing off the surrounding environment. By marrying the aero-stator wind capture with solar surface cladding, the passive tank surface becomes an active engine, securing a continuous 24-hour trickle of kinetic and solar energy regardless of the weather. We route that continuous trickle of energy down to the ground and feed it into a bulk energy storage system, or BESS, specifically a 60 kilowatt-hour lithium iron phosphate battery enclosure. The bulk battery acts as a slow fill reservoir. To prevent thermal stress from a fast charger's 100 kilowatt drain, we insert a hybrid energy storage system. A 1.5 kilowatt-hour electrostatic supercapacitor instantly absorbs the millisecond pulse demand, leaving the 60 kilowatt-hour chemical battery perfectly insulated from strain. By combining electrostatic capacitors for raw, immediate power with chemical batteries for deep, bulk storage, the hardware completely decouples low-speed generation from high-speed delivery. With the bottleneck resolved, the tower can deliver its 46 kilowatt-hour daily yield in targeted bursts. This is enough to provide 3 15 kilowatt-hour commuter fills every day, enough to cover 150 miles of total driving range for the community, entirely off the grid. Meanwhile, the parallel hydrological system continues to run. Remember that 17.3 psi of gravity head? That pressure silently pushes the 28,000 liters of condensed drinking water out into the surrounding soil, irrigating an entire landscape without a single electrical pump. We direct that gravity-fed water straight into high-density moringa groves, which produce crude protein, and down into a tiered polyculture aquaculture system that yields hundreds of kilograms of fish and freshwater prawns annually. This design transforms the structure into an apex node, fueling modern transportation and sustaining a decentralized biological food web from one tiny structural footprint. A full multi-utility retrofit, including the aero-stator, 60 kilowatt-hour storage, and charging hardware, costs roughly $53,650. While significant, it represents a fraction of the $1 million capital required for a traditional gas station or a utility-scale grid extension. If a community links just 3 or 4 of these retrofitted towers together on a shared DC microgrid, the system scales naturally. It creates a localized, completely self-sufficient communal fueling and water hub. This is the core thesis of the neo-pioneer movement. We do not need to bulldoze our natural environment to build a highly advanced, resilient future. By applying rigorous scientific optimization to the mundane structures already standing in our cities, we can engineer our way into a secure, self-sustaining future for any community in the world.